students. Today's discussion on microcontroller lab experiment number 5 code conversion. Today's discussion will be on these three programs: BCD to ASCII and vice versa, hexadecimal to ASCII and vice versa, hexadecimal to decimal and vice versa. First, let's try to understand how we can convert binary coded decimal to American Standard Code for Information Interchange and reverse process. Let's take a first example how we can convert ASCII value to the unpacked BCD value. By taking some example like 35, which is a ASCII value, in order to get the unpacked BCD equivalent value 5, we have to subtract from 30. A simple process to convert from ASCII to unpacked BCD. This is the process we have to use to convert this equivalent ASCII value to the unpacked BCD. Similarly, from unpacked BCD to ASCII, which is a reverse process, again say the unpacked BCD value we are assuming 6, and in order to get the ASCII equivalent value 36, we have to add 30 to that. This is the simplest process to convert BCD to ASCII. Similarly, for a packed BCD value, see, in order to get 56, which is a packed BCD value, the ASCII value, if they give by assuming 35 and 36 as in two ASCII value examples, in order to get the packed BCD starts from 10 to 99. So, in this regard, in order to convert ASCII to packed BCD, what we have to do? We have to first consider the values, two values, then subtract each individual value with the 30. Then once we get the result separately, which is unpacked BCD value, then a higher byte of a data need to be swapped. So you have to convert this to 05 to 50. Then add with the lower byte of a data. Then together which gives you a result of 56, which is a packed BCD. This is a simple process to understand ASCII to packed BCD. Similarly, from reverse process, packed BCD to ASCII. If the value which they have given, which is a packed BCD value, and if I want to get the equivalent ASCII value, I have to first unpack the data. Now I have unpacked the data by using a masking process. We'll see in detail what is masking process while writing the code. Once you convert the given packed BCD to unpacked BCD, now it's an easy process to add 32 individual data. Once you can store the information in respective location. So this 36 and 35 is the two ASCII equivalent values for the packed BCD. This is the process. Let's try to understand how we can implement using a 8051 microcontroller instruction set. Starting from ASCII to unpacked BCD, if, as I already explained, the data is this, to get the unpacked BCD, you have to subtract the 30 value. Directly I am considering 35 data, which is moved to the accumulator, and subtracting accumulator with the 30, and storing the accumulator content in the 40H location, which 40H location stores the result, which is the unpacked BCD value. Similarly, for unpacked BCD to ASCII, considering the direct data 6 and adding 30 to that, which gives a equivalent ASCII 36 value, which is stored in the 40H location. A simple program to understand. Next, moving to the ASCII to packed BCD. In order to get the packed BCD, we should have two ASCII values. 35, assuming 35 and 36, which is stored in 50 and 51H location, and the result we are going to store in 52H location. In a similar way, we can observe here. First, this 50H location is moved to the R1 register. This 50H location is the starting address of the which stores 35 data. The at R1 indirect addressing mode is used here. The content of 35 the content of 50H location, which is a 35 data, move to the accumulator. Then subtracting accumulator, that means 35 is subtracted with this data, we are getting 5. 05 is the data. Now this data need to be swapped. So that's why I am using a swap instruction. Swap A, which does swapping the nibbles here, and which gives the 50 data here. This has to be stored in the temporary. This is a temporary result which has to be stored in some other register. I am using R2 register to store this value. Next location data, which is 36, I am retrieving here. Then again subtracting 30 here. Then already this 6 data is in accumulator, and temporary result, which is 50 data, is in R2 register. Now adding together 50 plus 6, which gives 56 package BCD value. Now it is in accumulator. After this, it is in accumulator. This has to be stored in the next location, 52 location. That's why I am incrementing R1 and storing the result in the 52 location. A simple way to understand ASCII to packed BCD. Next one, packed BCD to ASCII. This is the packed BCD data we are assuming. I have to first unpack this data and add 32 individual this data. The respective data 36 and 35 gives you 2 ASCII equivalent values. How to do this? First, what is the process used to unpack the given packed BCD? As I already told, we have to go for masking the particular byte, half nibbles. How we can do that? Again, assuming that the original data 65 is available in the 50H location, and content of 50H, which is 65, is moved to the accumulator. Now accumulator data is also stored in one more register called R2 register, because we are going for masking. So it may alter the original data. In order to save it somewhere again, I have to retrieve it again. So that's why I am storing in R2 register temporarily. Now this process is called a lower nibble masking by using ANLA at 0FH, which results in 05 data. Lower nibble is higher nibble is masked here to get the lower nibble unpacked BCD way. So in this way, I got this value 05 now. Then all overall LA at 30. Also, instead of this, you can use addition, add A with the 30 also. Add or both are allowed here. Now by adding 30 to that, you will get 35. This can be directly moved to the 51H location, which is a converted ASCII value. Now to get this value, we have 65, which is again have to retrieve from original here. So that's why R2 register is used here, which is moved to the accumulator. Now accumulator is holding 65. In order to get the unpacked BCD in this fashion 06, I have to swap it initially. Swap A, I have to go for swapping. So by swapping the data, what happens? It becomes 56. Now I can go for again by masking process. I will get the 06. Again adding 30H to the obtained data 06. As a result, you will get 36. This has to be stored in the next location 52H. So in this way, the packed BCD is converted to the two ASCII equivalent values 36 and 35. Next one, hexadecimal to ASCII and vice versa. It's also a very similar and a simple process to understand. Say 3A is a hexadecimal value. If I want to get the equivalent ASCII values, again I have to go for unpacking the data. Unpacking using masking process. I have to unpack the data. 03 and 0A is the unpacked hexa value. Now, based on the quantity here, if this quantity lies in 0 to 9, then I have to go for direct 30 data addition. I have to add 30 to that, equivalent value gives the ASCII value. Now here, this value is greater than 9. If it is greater than 9, then immediately I have to add 30 plus 7 to that to get the equivalent ASCII value. This is the process has to be followed. So in this way, you are getting 41, which is the equivalent value for 0A. You can refer the ASCII table in order to verify whether for 0A do we have the ASCII equivalent 41, which is available in the Google. Kindly Google that and you will find the ASCII table, and you can refer for each number as well as the hexa number what is the equivalent ASCII value. Similarly, the reverse process, ASCII to hexadecimal process. If for first case, if the value is say assuming 39, if it is 30 to 39, directly subtracting minus 30, and the result is 09, which is a hexadecimal equivalent value. Similarly, for case 2, if the value is greater than 39, say 41, start from 41 to some other values, then we have to say this is the 45 ASCII equal value I am assuming, then I have to go for subtracting 37 from this value. So as a result, it gives 0E is a equivalent hexadecimal. Let's see the implementation part of